Okay, we're starting chapter 5, which is all about trig identities. And in 5.1, we're going to be reviewing some stuff that we covered way back in 1.4, which were some fundamental trig identities. So I want to first of all just remind you of what an identity is. An identity is an equation that's always true if both sides are defined. Okay, so always true if both sides are defined. So an example of an identity might be something like x over x is equal to 1. Okay. Now, as long as this side is defined, which would be if x is not 0, it's always going to simplify to 1. So this isn't an equation where I'd probably be asked to solve for x. I just say, oh, that's always the case. Another example would be something like 2 times x plus 1 equals 2x plus 2. Now that's something that's always defined, and it's always true. Okay. If I did solve for it, I'd get that x could be any real number. Okay. That's different from a conditional equation. A conditional equation might be something like x plus 3 equals 4. That's only true if x is equal to 1. Okay. So it's only true if that condition is satisfied. Identities, on the other hand, are things that are always true as long as both sides are defined, and they can be useful because they give us options for how we can write things. So an example of a trig identity, I could just take the definition of secant. Secant of theta is 1 over, actually I'm going to write it as x, it doesn't matter, but is 1 over cosine x. Now that's a definition, but that's also an identity. Okay, so that is something that's always true whenever both sides are defined, which of course is whenever cosine of x isn't 0, so not at odd multiples of pi over 2. That's different from a conditional equation like cosine of x is equal to 1/2. That's only going to be true for certain angles. So conditional equations are the sorts of equations that we might solve, try to find all of the angles that make it true. Identities are things that are always true if they're defined, and they just give me options for the way I can write things. Now, having those options is why these identities are important, because sometimes being able to write something a different way makes it easier to work with. Now, unfortunately, one of the drawbacks about this section in this class is that where the identities really become useful is when you want to do calculus. In calculus, you're going to learn how to do calculus things. And sometimes doing a calculus thing to that might be simpler than doing a calculus thing to that, even though they're equal to each other. It's just easier if I write it that way. Now, of course, you don't know calculus yet, so I can't really give you any examples of why that's the case. But just having options for how I rewrite things sometimes makes things a little bit simpler. Here's an example. If I wanted to do 1/4 plus 1/2, well, 1/2 is the same thing as 2/4. Being able to write it that way makes it easier for me to do the addition. Okay. So being able to rewrite something, because 1/2 is always the same as 2/4, makes that particular problem easier. That's what's going to be the case with the identities too. We're just not going to really get the payoff of seeing, wow, this is so much easier when I use these identities, because in this class we're just learning the identities and learning how to work with them. But the basic idea is that writing something this way might make my life easier than if I write it that way. And the identities give me that flexibility. Okay. So I want to just review the identities. These are sort of the fundamental identities that we discussed way back in section 1.4. So we've got the reciprocal identities. Okay. So secant of x is 1 over cosine of x. That's the definition of secant. Cosine of x is therefore the reciprocal of secant. Now that's not the definition of cosine, because there are times when cosine is defined but secant isn't, so that its reciprocal is not. Okay. Cosecant of x is the reciprocal of sine x. That's an identity that's also the definition of cosecant. That means that sine x is the reciprocal of cosecant if both sides are defined. Okay? But at multiples of pi, cosecant is undefined, but sine is defined. It's 0. I'm not claiming that 0 is the reciprocal of undefined. I'm saying as long as both sides are defined, this is going to be true. But I don't want to take that as the definition of sine, because sine is defined at multiples of pi. Okay. And then we've got cotangent of x is the reciprocal of tangent of x, and tangent of x is the reciprocal of cotangent of x. Now, neither one of these is the definition of cotangent or tangent, because of course tangent is undefined at odd multiples of pi over 2. At those places cotangent would be 0. And tangent is 0 at multiples of pi, which is where cotangent is undefined. Okay, so only these two are actually definitions. The others, though, are all identities that are true whenever both sides are defined. Okay. Then we've also got our quotient identities. So tangent of x is just sine of x over cosine of x. Now that follows directly from the unit circle definitions of things. If I have an angle x, it intersects the unit circle at some point, capital X, capital Y, okay? And the unit circle definition is that sine of little x is capital Y, because this would be x, y, and 1, and just using SOHCAHTOA, I get y over 1. Cosine of x is capital X, that's adjacent over hypotenuse, and tangent of x, just using SOHCAHTOA, I would get y over x. This helps me to remember these are my unit circle definitions. But notice that's just putting sine of x on top of, this is a capital X, on top of cosine of x. So that falls directly out of the definitions. Okay. And if I have that, and I remember that cotangent is the reciprocal of tangent, I can say that cotangent of x then is cosine of x over sine of x. Okay. Now we're going to have a lot of identities that we're working with in this chapter. If you try to memorize all of them, you are going to be miserable. Know that one and you get that one for free. I think most people, if you know your definitions, you've got the reciprocal identities down. Okay? This quotient identity, okay, it falls right out of these definitions, so I think it's easy to remind myself of what it is if I ever forget. If I make sure that I know that one solidly, I get that one for free. Okay. All right, so we've got a bunch of other fundamental identities. I'm going to stop this video here. We've got two more types of fundamental identities, which are the Pythagorean identities and the even-odd identities. We'll talk about those in the next video.